Hi, Dmitry. How are
Hi.
you
Hi.
today?
I'm doing great. How are you?
Not bad. Just the second day of Devoxx. It's impressive. What have you prepared for
Great.
us today?
Well, I have prepared a nice talk, 2 hours long, about Kafka Streams and Spring Cloud. Hope everybody will enjoy it.
Yes, okay. I'll say you good luck. And for your audience, I'll recommend not to hesitate and follow our mobile application to choose to vote for your speech if they like it. So, good
Great.
luck.
Thank you. Okay. So welcome to this talk. My name is Dmitry Sergeev, as you probably heard. Here, I'm going to show you some cool things and discuss Kafka Streams and also Spring Cloud, because that's probably the most popular framework at the moment, and many of you work with that, and it helps to simplify things a lot. First of all, about me. So I'm challenging my neck in tech for 7 years already, and I'm very happy with the latter, not so much with the former. 100 of those years are spent with Java. Prior to my current company, it was everything related to IoT. Now it's not, so really very curious about new domains. Um, Not only Java, but also I'm passionate about urbanism product management. So in case you are interested in those topics too, I'm very excited to talk to you about, well, with some maybe online coffee cup about those topics too. And here I've got 3 books that I like the most from all the domains I like. So really, really recommend those. So let's start. The first question is, why Kafka? Have you ever wondered why is it called Kafka? Why is such a name? So Jay Krebs, who is the creator of Kafka, just told an interesting story about that. So he was creating a tool optimized for writing messages, and he started thinking, what name should I give to this tool? Like, it's about writing writers. Maybe it should be called after some writer. And in high school, he was attending lots of literature courses, and so he remembered Kafka from those courses, and he thought, Kafka, it sounds cool, and also it's a writer. So for writing system writer, it's, well, sounds good. Sounds good. Let's go with that one. So there is no much of a relationship, actually. It's just because it's writing writer, Kafka sounds cool. Okay, and let's go to the actual presentation. Well, we're going to cover these questions and topics here. First one is, what is Kafka Streams? What is it all about? What is it exactly? Then we're going to discuss true application architecture, meaning from what parts constitute the upstreams application? How do you design? How do you basically wrap your hands around what's not? We're going to do some live coding. We're going to write Kafka Streams application that uses Spring framework. It was meant to use also Raspberry Pi, but just, I was testing my code, this presentation, to make sure everything works, and I had this nice temperature and humidity sensor that just was working fine, but then it just died. So I thought, okay, let's buy a new one, right? I want my talk to be 100 like ready with all this cool IoT stuff going in there. So I bought a new one, and I tested this morning my code. Yesterday it was working, everything was good, and this one, like, now I have 2 of them, died too. So unfortunately, in this talk, we're going to mock our Raspberry Pi. It's actually nothing will change from the code perspective, but still, sorry, no Raspberry Pi in this demo. We will simulate one. Then we're going to discuss stateful and stateless processing. What's the difference when you need which one? Also, windows and aggregations, not the operation system actually, but more of a concept. Then how does it work with Spring? Of course, you want Spring, right? You want to simplify things. You want to integrate with existing libraries. Just know a lot about Spring. So yeah, there will be some Spring also. Also, an interesting topic, how time flies. It's not that obvious as it might seem. In Kafka Streams, there are some gotchas in there. Also, distributed transactions and deduplication made easy. Very interesting topic, a lot of debates and discussions going in there, and we'll see how it how we can solve some interesting problems with Kafka Streams. And last but not least is how to deploy things, how to make sure your production, your cool, nice code doesn't break in there just because you forgot to tweak some things when you deploy things. Okay, so what is Kafka Streams? Kafka Streams is a client library for processing, analyzing data stored in blah, blah, blah. It's a cool, nice definition, but it's too long, right? We like the shorter ones. Too long, didn't read. So Kafka Streams is just a library used by your application. So it's just, a regular dependency you add to your Maven, Gradle, or just don't call anyone, Ant project, and you use it. So it's like a jar, you use in your library, just a library. Actually, it's not something something supernatural. Under the hood, Kafka Streams library uses Kafka producer and consumer APIs. So it's actually a library that works on top of Kafka, right? It uses data in Kafka topics. So everything you already know about Kafka is perfectly matches like Kafka Streams when you're going to learn it, when you're going to use it, because a lot of concepts are just they are basically the same things in there. It also provides API for processing data in Kafka. So just what I told now. Those are the APIs, the functions, the classes you use to process data that flows in Kafka topics. It also contains solutions of the data stream processing problems. So aggregations, state, recovery, scaling, a lot of things you are going to develop on your own if you don't use Kafka Streams, but you do want to do some processing of data that flows in Kafka. No need to develop that from scratch. A lot of those things are already in Kafka Streams. So what are the use cases? When can you use Kafka Streams? So there are a lot of use cases, but I mentioned here the most popular ones, probably the most, just those that are easy to get with Kafka Streams. So first, website and mobile app activity analysis. So for example, you have your clicks, your impressions, views, you collect a lot of information on your website, and maybe you have a really big website and Kafka Streams help you serve even those. So you collect all this data, and for example, your business analytics, your marketers, they're coming to you and they want to get some most popular items in the last 5 minutes, or most popular comments in last 5 minutes, or something like this. So Kafka Streams give you an ability to generate this kind of insights from data in real time. So there is no need to do some batch processing, to wait 2 days and then present some batch results to your marketers, and they tell you, I know I'm not interested anymore in this thing. I needed that 2 days ago. So that's not a problem. With Kafka Streams, you can do this in real time. Then processing and aggregation of application logs, also very popular use case. So you're collecting a lot of logs probably if you have a considerably large system. And here, same thing, you can generate insights in real time. You can trigger some alerts in real time. Anything you can imagine, you can derive from your data in real time. It's about Kafka Streams. Also, an interesting use case that comes from a friend of mine, streamed content generation. So my friend is working in a media company. They're just generating some news things, and they need to be on the edge, and they need to show things faster than others. And what they do, they actually parse some RSS feeds, some other websites, some Facebook groups, different points that can generate some new information that might be interested to a wider audience, and they feed all this data into Kafka Streams. Then they assign an importance or value or some metric that tells them that this is an interesting thing, and they maybe combine some news, combine some things, and they post it on their website. So their website is automatically generated using Kafka Streams in real time from all the news around the world, and they are basically they're the first ones. They combine all the information that users are interested in, and everything is in real time, very fast. And of course, there might be a lot of other use cases. I'm pretty sure you will find one in your project or in your past projects, and of course in your future projects after this talk. So what Kafka Streams gives us out of box? It gives us fault tolerance. So if your application just died in the middle of processing, It's not a problem. With Kafka Streams, you can actually handle those cases. You can reprocess data. You can make sure nothing is lost. You can make sure that you catch up from where you stopped, from where you failed, and all the things comes out of the box. Also scaling. So because Kafka Streams is built on top of Kafka, right? It's already a system built for huge loads, for massive amounts of data. Kafka Streams continues this path, and it gives the same thing. So there are there is a good, nice architecture under the hood that gives you ability to scale just enormously. Also, what differentiates Kafka Streams from other similar tools or libraries is exactly one's processing semantics. This is something that comes actually from latest versions of Kafka. This is not something that comes by default. So this is very important. If you saw here that that Dmitry told you there is exactly one's processing, and you just simply created an application and went into production, not so easy. Make sure you enable some properties, and we will see which ones in a while. Also, it gives you aggregation operations like windowing, count, many cool things we will see, and we'll discuss what exactly it means. Maybe not anyone knows what is windowing, and that's totally okay. Then late arrival records handling. What if some records got stuck because of, what if your an internet got slow, something got disconnected in the middle while some information was arriving to your system, and it arrived late, a couple of hours after, or maybe days or something. And in many cases, you don't want to lose this one. You want to make sure you can process that, and it can get into your system in a good way. This is also possible. And also, there is an ability to extend default functionality. So if you're missing something from default Kafka Streams API, it's not a problem. You can extend interfaces and things and make some new functionality that you need on your project. And we'll see that as well. So most interesting and most complex probably thing here is architecture. So there are three concepts you need to understand with Kafka Streams. The first one is processor topology. It is actually a graph, a directed, acyclic graph that defines the logic of processing. So imagine a graph, or just look at it on the right. You have some information that flows into this graph. On top, right here, I have Kafka topics on top of the slide, and some data flows into the graph that you defined that somehow process the data. So the data flows into this graph that you defined. We'll see how to do this. It gets into processors as a stream. So the processor is a node on this picture here. It's a node in your graph. It is actually a function that can process the data in some way. You can think of them like Java Streams API, right? All those map, flat map, for each, and all those things, they are very similar, and they actually sound the same, and they look the same, and work almost the same in Kafka Streams, and those are your nodes here. So each function like map, flat map, here on a node, here in a graph, is a node that functions and somehow processes the data. It consumes the data from a stream, and a stream is an ordered, replayable, and fault-tolerant sequence of immutable data records, where a data record is defined as a key-value pair. So each message in Kafka Streams, as in Kafka, is a key-value message. And the processor, your function, your for each or map or flat map, processes these record one by one, and it transforms, it creates, it merges them, it maybe splits them, and it sends them downstream through this graph to other nodes, and in the end it leaves your graph, right? In the end, you maybe consume, you can send an HTTP request, you can send it to another Kafka topic, anything else, like, so the data gets into your processor topology, the graph that defines the processing logic, through so-called source processors. So if you will be reading Kafka Streams documentation, source processor is the entry point of your computational graph. And the sync processor on the bottom here on this slide is actually last node, right? Not last node in your processing graph. That's where everything stops, where data leaves your graph, or where you just consumed with some terminal operation like for each, for example. Topologies, where's the premise Spring Boot, right? It just, I wanted to start with a starter or something like this. And before we get there, let's understand one important thing: how processor topology, this Kafka Streams concept, matches your understanding of microservices, of application instances of your Spring Boot apps, right? So here on this slide, we have an orange frame. So an orange frame is a boundary, and you need to really understand this one, is a boundary of topology and microservice. So topology is always within a microservice. You cannot have topology that spans multiple different types of microservices. So topology is always inside a microservice. It is inside one type of your microservices, inside one one microservice. And there might be combinations because of this. And we have them. There actually might be three combinations. The first one is when you have your topology with multiple processors inside a single microservice. So here, orange frame, your microservice actually contains a lot of different, operators, things that process the data, and you have the whole, this whole topology in there, right? The second case is when you actually split a big topology into multiple ones. When you have many small topologies, each containing, let's say, one operator, one function, one transformation. And in that case, you have a topology, right? In each microservice, you have many microservices. So each node here corresponds to a microservice. And still, you have, high-level topology in your terms. So you still have a graph, right? You have this graph. But in terms of Kafka streams, topology is only within each microservice. But the whole one, the big graph in there, here is just your high-level thing. You can call it topology, but it's not topology in Kafka stream terms. On the right, it's a combination of both, actually, right? You can have few functions in one microservice, another few in another microservice. And now you have two topologies, one big graph still, right? But two Kafka Streams topologies and two types of microservices. Hope you got this one. Yeah, it probably sounds complicated, right? You saw Spring word in the name of this talk, and you thought there should be a starter. I hoped to see a starter, and it just should go. So you can exhale. There is a starter. There is a project actually in Spring ecosystem called Spring Cloud Stream Kafka Streams. It's such a long name, and I bet I will make some mistakes. So don't blame me. So there is a starter that sounds something like this, and under the hood, the Spring starter uses Kafka streams. So there is a Kafka stream library from Apache in there. And also there is a Spring for Kafka library. So Spring, of course, has some wrappers, some APIs, some simplifications for working with Kafka, and those are used in this starter. What it does, it automatically creates and configures a topology. So you're not with Kafka with Spring Kafka streams. You don't set up topology on your own. You don't use topology API for Kafka streams. So the starter will do it on its own. Also, from latest versions, it supports functional paradigm. So, and we'll see that because we're modern, right? We want functional. Okay, this is enough theory, right? The talk promised some live coding, and we'll get there soon. So before we start coding, we probably need to plan, right? I hope you do. Yeah, I hope you're doing this. Yeah, I hope you're planning before you're going and coding. So what we're going to create is a simple application that consists of three parts. The first one will be the weather sensor application. It will be written in Python, and we are not going to spend time there. It's not interesting in our theme here. So this weather sensor collects temperature and humidity from some sensor, and it sends measurements to a REST API over HTTP. So the second part is a REST API application. Very clever name here. So it's just a simple application, with all those Spring controllers, and just a simple HTTP REST API that collects measurements sent by a weather sensor and forwards them to Kafka. So it's just a very simple one. Get data from HTTP, send them to Kafka. it's there because maybe you want to add, some security. You want to secure your APIs. Maybe you want to enrich data. You want to add something to your weather sensor message and send it to Kafka together. And last part, the most interesting for us here, is Kafka Streams application. So it will be a separate microservice that will consume data from Kafka topics. It will consume those temperature and humidity measurements. It will process them somehow. We'll discuss how in a moment, and it will trigger alerts. Yeah, actually, as you can see a note on the bottom here. You can actually get rid of the second one. You can actually make weather sensor send data directly to Kafka. But I decided that this architecture is probably more popular, and it gives you, it just solves more use cases, because, for example, you can replace weather sensors with the web browser, right? And it's just, it's more usual to collect something over HTTP from the web browser, right? Okay, so let's start doing things. First, we're going to bootstrap the project, and I'm going to do everything from scratch, so that if I face some problems during coding, you'll see them, and if you face them too, you'll see how I solve them and what they actually mean. Yeah. So sorry, let me hide this thing here. Going to create a new project here. File, new project. It's going to be Maven project with Java 15, right? Why not? Why not use Java 15? Let's call it Kafka Stream Devoxx. Let's give it my name as a group ID, an artifact case stream Devoxx. Okay. Yeah, I want a new window. Okay, we got our project. Seems to work. It looks like it there. It was an easy step, right? So just hope you understood this one. Next step would be to actually create our REST service, send some data to Kafka, collect it from the measurement sensor, and there will be some common library that I will explain in a while. So let's do first thing. Let's create a submodule here that will be our REST API application that will collect data from the sensor, and it will send it to Kafka. Here I'm going to use Spring Initializer, Java 15. Let's give it the same group, but just subgroup K stream Devoxx. REST, very simple, Java 15. Everything else looks good. I'm going to use Lombok just to save some time. This one needs Spring Web, right? What else? It also needs Kafka. Spring for Apache Kafka. So Spring Web for our REST API, Spring Kafka for sending data to Kafka, and Lombok for saving time. Okay, it's there. And let's add this one as a submodule here in Maven, right? Also, I want to enable auto reload for Maven, right? Just don't want to click on this thing all the time. Okay, so it got our REST application. Okay, it sees it's a source. Good. What you don't like here? Let's aggregator. Okay, doesn't matter. Let's create our simple REST API. We will call it weather controller. So it's a REST controller with a mapping. Actually, I have here another project that I tested with, right? And here is the actual code of the sensor of the Python application that emulates the weather sensor that collects some humidity and temperature and so on. It just sends them. I'm not going to show you this code. It's very ugly. Don't write code in that way. I did it just because I could. So this is the API it sends data to, our weather sensor. So let's use it. It sends data over POST, so over HTTP with a POST request. So it's POST mapping, public, nothing in return, collect let's just call it collect. Now we need to have a class that represents our measurements. Let's call it measure weather measurements. And I'm going to create this class actually in a common library because we will have, we'll just use the same class in our Kafka Streams application. So let's have a common module in here. Module will be just plain Maven, stream Devoxx common. Okay, in this module, I'm going to also use Lombok. By the way, I'm going to I'm going to write POM files, maybe not in the best possible way. Just don't blame me because we're going to save some time here. I'm sure you're good at writing POM files. Yeah, so let's create a class here, right? What was the name? Weather measurements. Package. There is no package. Why there is no package? Let's create a package. Let's move it in there. Good. So it's it didn't get Lombok here, right? Why is that? Probably because the POM file. Yeah. Let's copy. I'm going to copy some things just to save time here. It probably complains because of the Java version, because it's 15, and maybe because it's not configured very well. Just going to copy and paste some things here. So let's make this thing here in the root, and just let's copy the same thing to here. Just make sure it works. Rest common, okay. Okay, it's downloading some dependencies. Let's see if it sees. Yeah, I know. You know why? Because there is no version. 1.18.16. You probably already know that, guess that, right? That's I who is spending your time here understanding these things. Okay, while it's downloading dependencies, let's see which what is the body of the message, right? So our sensor sends this type of these fields. It's device ID. We'll have a few of them, so we need device ID to differentiate between them. It sends temperature Celsius, humidity, and a timestamp. So those are the fields we need to have here. Private long device ID, private float temperature Celsius, float private float humidity, and this one is actually an instant. Yep. Okay, why it takes so long waiting for one impaired completion? It's got stuck here. I hope my internet is working. Okay, impaired here, instant. And this one actually also needs some annotation because it's in timestamp, right? And we want to parse it so that checksum can parse this one from a JSON. So I'm going to add one more dependency here. Checksum data type GSR 310. And yeah, it's JSON format as I remember. Let me just check this out and probably just copy it from there. So this one is needed for basically parsing our thing. So back to our controller, add dependency on module common, then import class, Yeah, I had it. No, why is it complaining in there? Everything looks good. Okay, so we got our measurements here. It's actually request body, right? Next, we need to send this thing to Kafka. So I'm going to have sender service is a good name. I think not, but still measurements. Create field final sender service. What's that? Let's create this class. Okay, we got it. Now let's edit, of course, so we'll be able to auto-wire it. Create method. This one is going to be service. And here we actually need Kafka template private final Kafka template. So this is a class from Kafka, from Spring for Kafka that sends messages to Kafka. Very obvious. The message key in Kafka is long, our device ID, and the body is weather measurements. And it's very simple. Send. We give it a topic, a key, and a value. So the topic will be weather data. The key will be measurements get device ID, and the actual message itself. As you see, it's complaining because we need to define a bean for this Kafka template. So we're going to create a class called Kafka config. It's going to be configuration. And so we need to have a bean public Kafka template long measurements, Kafka template, return new Kafka template. Yeah, it needs a factory to instantiate itself. It's a bean, of course, it's a bean. Now we need to give it this factory, another bean in here, bean public Kafka producer factory. Producer factory in here. This one is new default Kafka producer factory. It needs another arguments here. Producer configs. It needs a serializer, new long serializer from Kafka. Also, it needs JSON serializer because we're going to send our messages serialized as JSON to Kafka. And the last thing here is producer configs return map of producer config bootstrap servers localhost 1992. Okay, seems legit. I hope it should work. So let's start our REST application. No, one more thing. Let's make sure it actually works, right? Let's add some logging in here. Log send. What am I writing? Sent and message we sent. Good. So now let's start this application. By the way, I have my Kafka running in Docker Compose. Let's make sure it works. It runs. Pose up. Okay, I'm starting Kafka and Zookeeper here because we need some to test it with, right? And another thing is I'm going to launch this Python application with a sensor that sends some data. And we hope, you see, it collects data. Still collects it. Why it doesn't send it? should be a log saying send. Or Kafka just died. Okay, you know what? Probably because some conflicts with an existing one. So I'm just going to remove it completely. Yeah, so now that we have Kafka running, let's go and create those topics. It's here, being. So inside Kafka and all installations, you usually have very useful tools. If you didn't know about them, it's very useful. One of them is Kafka topics, sh, that we can create a topic with. Just in case you don't see what I'm writing here, let me enlarge it. Localhost 1992, topic weather data, right? Create partitions 1, replication factor, it'd be 1, 2. What? Already exists? Okay, exists, then fine. So our Kafka looks to be running. Yeah, send weather measurements. You see, so we're sending data to Kafka. We see our Python application tells us send the measurement, so it works. And make sure in Kafka, always make sure it actually sends data. So there is another tool here called Kafka console consumer sh, right? Let's make sure we see those messages in Kafka, and the group will be some group. Yeah, so those are the messages our REST application, our sensor sends to REST application, the REST application sends it to Kafka. Good. So now we have the first part of the chain. Just let's stop things here. Okay, what's next? So we got REST service sending to Kafka. We got Camel library. Next is Kafka Streams application, the actual thing, right? So we need to bootstrap one more module here. It's going to be called Streams module, Spring initializer. Same package. Streams 15. Good. So again, Lombok. Here we actually need cloud stream dependency. Lombok, cloud stream, and that's probably it. Everything we need from the initializer here. Okay, streams. Let's add it as a module. And let's make sure all the things are in there too, because I had some problems with that when I was testing. Just going to copy it in there to make sure all those things works. Build, I already have build, right? I already have plugins. That plugin in here, properties, good. So as you see, when we generated a project, it actually added one interesting dependency, Spring Cloud Stream, but it's not enough. We need one more. One more dependency is called org Spring Framework. Why auto-completed some things? Spring Cloud Spring. We need Spring Cloud Stream binder Kafka Streams. So Spring Cloud Stream gives us some APIs, some interfaces, but we need an actual implementation of some of those interfaces that work with Kafka Streams, because there are also other tools in there like RabbitMQ, for example, but we want Kafka Streams. So we add this as an implementation. And if you go here you will see that under the hood, it uses Apache Kafka Streams. That's what I told you. Okay, what you don't like here? Duplicated properties. I agree. You're always right, I'm always wrong. Okay, Streams application. We have it here. Let's try to run Streams applications. What we'll see. So it's starting. And it shut it down. So because we don't have any processing logic in there, it just started and stopped. It actually also probably connected to Kafka, so it just stopped. So the next thing we need to do is actually write some code, right? Some processing logic. And let's discuss what exactly we're going to write in there. So I told you we have some temperature information, some humidity information from our weather sensor. We're going to calculate average for 5 seconds of temperature and humidity. And if those averages exceed some threshold value, then we fire an alert. So it's a nice implementation, let's say, of alarm of temperature alarm system in your home. To make sure you don't have fire in there. And in order to write this, we'll need to understand two important topics. First one is k-stream. So, and the second one is k-table. When you have messages going one by one, it's a k-stream. When you have aggregations, like here, average, you need k-table. And let's discuss what it is. Those both things. So stream is probably more familiar to you. It's just a stream, like a sequence of messages in a Kafka topic. Like here, you have a message with the key being Alice and a value being 1, and then you have a message Charlie 1, and so on and so forth, one by one. Messages and topic, very easy. This is called a stream, or a class that represents that in Kafka Streams API is called k-stream. Then a k-table is actually a snapshot of all values, of all latest values for all keys in a stream. So if you will play messages in a stream one by one, putting them into a table, like here, Alice goes to Alice 1 and Charlie goes to Charlie 2 in a table. Then when you say Alice again, you just override the existing value, if any. Right? So the table represents latest values for each key in a stream. And what's interesting is that is actually a duality of those concepts. So at any point in time, you can go from a stream to a table, right? Just as we did that. But you can also go from a table to a stream. So if you will iterate over every row in the table, and push it, let's say, to a Kafka topic, you will get a stream. So like here, we have a table and we just push it, iterating over those rows, and we get a stream. So at any moment in time, you can convert k-table to a stream, and you convert k-stream to a table. Now having this basic knowledge, let's go writing our first function that will calculate average value. What's here? Why is it complaining all the time? So the first thing we need is average config processor config. So first of all, functions with the latest value, they're usually defined, with the latest version of Spring Cloud, they're usually defined as beans. So our processing function is actually a bin in the configuration class. It is public. In our case, it's function. So we use just plain Java functional interfaces. Why is it function? Because function consumes something and it gives you something in return. So in our case, we consume messages from weather data topic, right? We calculate average and we send average to the next topic. So it's a function. A function that takes k-stream, just as we discussed, a stream of messages with a key being 1 and a device ID and a value being weather measure. I need to take this, right, and I need to add it as a dependency in here to this model. Add dependency. Good. Now import. and now import. So we get KStream and we return KStream. But here the key will be same, but the new object will contain average information. So it's weather measurements average, right? Let's create class this one, and we'll populate those fields afterwards. And we need to give it a name to this bean. It will be averager processor. Good. So let's start writing. Because it's a functional interface, we have an input here. This input is actually we need to process data. So we have our temperature and humidity messages in weather measurements class, and we need to first of all we need to group by key, because we want to process the average information for each device separately, and the key here is our device ID. So so we have our group by key. Then we need to create a window, and this is a new concept that we need to discuss here. A window. What is a window? A window is actually a set of messages in a topic on your time axis that you process as a whole. For example, 5 minute window is a set of messages for 5 minutes that you can process as a whole. You can calculate an average for them. You can sum them up and so on. So for example, in this picture here, we see 2 keys. So 2 keys in the Kafka topic. The first one is the green. In our case, let's say it's device ID number 1, and the blue is another key, device ID number 2, for example. And we have temperature measurements over time that are sent to our application, to our this string function that we just wrote. And we want to process each 5 minutes, or in our case, it would be 5 seconds, as a whole. So it's a window. Windows they also have some interesting characteristics in Kafka Streams. First of all, windows, they emit value each time there is a new. So even if the window hasn't finished yet, if there is a new record within the window boundaries, it will be emitted downstream. So the next topic in our case will receive this message, and we will need to find this this characteristic, because we only want to have a result of aggregation only after the window was closed. And for that, we'll use an operator called suppress. You'll see that in a while. So now that we have a basic understanding of windows, let's discuss stateless and stateful processing. So windows, as you probably might guessed, are stateful. So they have some state over. We say we want to have average over 5 minutes. In order to calculate average, you need to get amount of records per 5 minutes, right? And divide them by, we need to have a sum of temperature, for example, for 5 minutes, and divide it by amount of temperature records that we got during this time. And somewhere we need to store how many records we have seen so far. It's a state that needs to be managed somehow. So it's a stateful operation, state. Another type of operations are stateless, right? Like for each, right? When you're doing for each, you just somehow apply some function to your incoming record, and that's it. That it just goes in there, and that's fine. No statement in here. So for example, stateless operations are like this: send a message to another system or write a log. And examples of operators, it's filter, map, for each, or print. Stateful, and as I told you, count amount of messages, join few streams. So it's possible in Kafka Stream to actually join multiple topics and process those messages. Yeah, so examples of operators: aggregate, count, and reduce. And it might sound obvious, but Kafka Streams store state in a state store. So it's actual name of the concept in there. It's a thing where it stores state. So state stores are actually stored in a local file system using RocksDB. So there is a database under the hood on the file system that stores this state. By default, it's located in a temp folder. It is actually baked up to a changelog topic in Kafka to restore a local copy after restart. So because it stores this, it stores a state in a local file system. What if, for example, in Kubernetes, your pod just died and it got rescheduled on a different machine with a different file system, right? And there is no, did I lose my state? No, because it's also baked up to a changelog topic. So local file system is used for doing that quickly, right? For retrieving everything very quickly. No need to go to Kafka and so on. And changelog topic is used to reconstruct a local database when you got rescheduled somewhere else, your application. And also, it's very important to understand that you need to have application ID set in your Kafka Streams application. It's a property. I will show you that later on. It differentiates different like names of the changelog topic and so on. For example, we have changed the format of the data you store in the state store, and it's maybe not backward compatible. In that case, you need to change application ID, so it will use another name for the state store. Okay, let's get back to code and now try to code all those things I mentioned. We're going to finish the average processor. We're going to write the alerts processor, and we're going to launch everything up. So we got our weather information grouped by key. So for each device, you'll see that it gives us k-group stream. Now we want to have a 5-second window for each device, and for that we use time windows of duration of seconds 5. Another thing here is a grace. So grace is amount of time Kafka Streams will accept late arrived messages. If you remember, I told you you can do late arrival message handling in here. So grace is a, let me go to a picture here. So here on the picture on the right, you have W10 and some messages in the window. And you see some of them are, the last one on the right is discarded out of grace. But the third one is actually not, even though the window was closed already. That's because a grace time was configured. In our case, we're just going to set it to 0. No need for grace time. We just simplify things. So if something arrived late, we just discard it. So now we have time window k stream. So a string of messages by 5 seconds for each device, and we're doing aggregate. Now we are actually aggregating this thing in a window. So we need to give it some functions. I'll discuss which ones exactly. So first of all, we need to have some class, some object that stores this intermediate state while we are aggregating. And we'll call it very simply intermediate aggregation state. Let's create it right here. Private static class, intermediate aggregation state. Class, forgot you name it class. Data, all args constructor, no args Lombok to the rescue. So intermediate aggregation state is going to store information that we need to calculate average. So it's amount of records and their sum. So it's temperature count, how many temperature records we got, their sum, temperature sum, also amount of humidity records, then amount of sum of humidity records. So later on, when we collected all of them for our 5 seconds, we're going to divide sum by count and get an average. And here, just return new intermediate aggregation state. Now, the actual thing that does aggregation for a window, it actually returns key value long weather measurements. It also takes a window. Yeah, no, sorry, I'm wrong. I'm wrong here. It gives us the result of the aggregation like this. It takes message key. In our case, it's device ID. It takes a new message that comes that we need to add to the aggregation, and the previous aggregation result. So we are going to return new intermediate aggregation state. So temperature count, what we're doing intermediate aggregation state, get temperature count +1, right? So we got a new message here, +1. Then intermediate aggregation state, we get a sum of temperature we saw so far, plus we add temperature that we got here. Then humidity, and humidity sum. Okay, so this function, right, will be applied to each incoming message in our window, and it will add it to the aggregation, add it to the sum and to the count. Another thing is, because, as I told you, we need to use a state store. We need to Kafka Streams need to store this intermediate aggregation state between retrieving different records from Kafka. We need to help a little bit with that. So we say that this state store should be materialized with a serializer of type. The key is of type long, and the value is of type JSON serialization, and we give it a class. Okay, now that we aggregated them, we have those aggregated values. We need to do suppress. So if you remember, as I told you, by default, Kafka Streams emits a result of this aggregation downstream each time new record is received, even if the window itself wasn't closed yet. So for that, we use an operator called suppress. So we say, please don't send aggregations downstream unless window has closed, and also we say we give it a size of the buffer, the maximum size. You know, you can configure that if you got too much messages in there, then okay, I'll let you send this message downstream. But in our case, we use unbounded, so it will just keep it there forever, until the window was closed. Then you'll see that because we were doing aggregation, we got a key table, right? Where device ID is a key in this table, and the aggregation result is a value. So now we need to convert it to a stream. Remember, I told you at any time you can convert key table to a stream and vice versa. And then we do map. We need now to take those intermediate aggregation state for each device and calculate the actual averages. Very simple. This average, with key value being long and the container for our average, right? So we return key value pair where device ID is still being the key, and the container that holds the actual averages. So let's add them here. Let's add a device ID in there, just make sure we have it. So what do we have? We have floor. We have, let's do double temperature average, right? And private double humidity average. Okay. Yeah. So device ID still long windowed key. Temperature average should be simple enough. So intermediate aggregation state get temperature sum divided by intermediate aggregation state get temperature count, right? And same goes for humidity. Okay, seems to be the thing we wanted, right? So now that we have average processor, let's write the next one. Let's write the one that will be sending alerts. Or you know what? Let's try to start this one first of all. So let's start our streams application. Let's start our REST application. Let's start our weather sensor. Okay, so see now that our Kafka Streams application doesn't shut down anymore, because now it's so that you have a function, right? You have a function that does something, but you have probably mentioned but we didn't define any topics in Kafka Streams application, because how does it know which topics to use here and which topic to send data to? And the answer is know-how. We need to basically define this thing. So let's stop it. Let's go to application properties. Then I'm going to actually change to YAML. And we need to define some properties here. First, we need to define Kafka. We need to define cloud stream bindings. So each function, each processing function, like this one, like averager processor, is actually a binding in cloud stream terminology. So you take it, the name of the function, the name of the bin. You say in 0, which means first incoming argument, this K stream, because as you remember, you can merge a lot of them, but in our case it's just one. So this incoming one destination is weather data. That's the name of the Kafka topic. And out, meaning where we're going to send data to, out 0, we're going to send it to a topic called weather aggregation, right? Another thing is that you can also define things like Kafka boots server hostname and port, right? But by default, it connects to localhost 1992, which is good. In our case, that's totally okay. So let's restart it once again. So what we are going to see, we want to see aggregation, right? I have restarted wrong application. So we want to see data in the weather aggregation topic that has aggregation. So we're going back to Kafka console consumer, and we're going to listen to another topic here. And we want to see some values here. So 5 seconds, right? REST application sends data. Okay, opening store, something is going on. So it's opening the store for aggregation, right? And we see aggregations. So this is the topic with aggregations, and we see temperature average and humidity average. And you may notice that even though we're sending data pretty often, it's actually 1 second or something like this from the sensor, we are not getting them here. and you'll see that we'll see few messages here in a batch, right? But I promised you real-time processing, no batching. That's actually possible, but here by default it uses Kafka commit interval of 30 seconds and stuff like this. So everything every 30 seconds are committed to Kafka at once. That's why we see 6 messages, right? Because 30 seconds divided by 5 seconds for Windows is 6 messages here. And I will show you how to change that so that it's really real time and one by one. Okay, we have our averager processor working. Next thing is create a processor, another function that triggers some alerts if temperature is too high. Let's call it alerts processor config. Same, it's configuration. And we're going to define a bean, public here actually it's consumer. It's interesting, it's something different. So we had function previously, here function, but here we have consumer. And the reason for that is that alert processor is going to consume data from a Kafka topic and just see if it exceeds the threshold and just write a log. We're not going to send the result to another Kafka topic. So it's a sync processor, right? In terms of Kafka, it's a terminal operation. It's just like a for each. So it consumes a stream of long and average here. Import and alerts processor, return input, and guess what? It's just for each, right? It's just a for each action. We're just taking like a record from Kafka. Oh, it's actually a pair. It's probably a pair. It's probably a key, right? And a value. So a value here is our aggregation, our average, and we're doing a very simple thing. If value get humidity is more than, let's see, what values do we have? Humidity 50, 51, 50. Okay, so if it's more than 51, then just let's do some log. Let's do log barn threshold reached and a value. Okay. 51D is probably, it's fine. Okay. It's a bean, right? Don't forget to define it as a bean. And let's restart our application. No, one more thing. We forgot to do the same thing, right? We need to tell our second processor where to take data from. So in our case, it's alerts processor in weather aggregation, right? So what is out for a previous one is an input for this one, and no out here. Let's start it. Boom, exception. What's here? Multiple functions found, but function definition property is not set. So when you define multiple functions in Kafka Streams in Spring Cloud, actually you need to help it a little bit to make sure you want all of them, and or which ones you want to have actually. So you need to define this small little property here, function definition, Spring Cloud function definition. And the function names, and here you need to put function names separated by a semicolon. Once again. Okay, threshold reached, right? It works, it works. But there is one thing you really need to always set in the settings. And the thing is, it's, I think, streams binder functions, this thing. And you need to take each function and give it an application ID. Remember, I told you that application ID is actually used as a Kafka group, consumer group, and also used as the like a prefix, the key for the state store. So if you have a state store in multiple functions, there might be problems, and there also might be problems with committing your offsets and other things and fetching data. So always give it an application ID like this. And so in future, if you change, the class, the structure of the object you store in a state store, you can just bump the version here and push it to production, and it will use another one. It will not collide. Once again, start. Okay, so we see messages threshold reached, right? So which means that our second processor works. It gets some data, and it works, right? So going back to our slides, yeah, this one we covered, this one we wrote. Another thing to understand are the different concepts of time in Kafka Streams. So you might be wondering, I told you we have created a window of 5 seconds in our code, right? But what is the time of an event? Meaning each record that gets to through application, what's the time of that record? Is it the time when our application received it? Is it the time when Kafka received it? Is it the time when it was created? Like if you remember, we added some timestamp initially into the class we're sending here. No, sorry, it's a wrong project. Here, timestamp, right? But we haven't used that, and that maybe Kafka uses it automatically, or so. This is something that is not clear at the moment. So there are actually 3 types of times in Kafka streams. The first one is an event time. It's a moment of time when event happened on the source. So in our case, event time is this timestamp that we send from a device. Then processing time is a moment of time when the message is processed by an application, right? It's also legit. And the ingestion time, moment of time when the message got into Kafka. So in order to use one of those, you actually need to implement timestamp extractor interface and help Kafka Streams a little bit to basically understand what is the time of an event. And we're going to create this interface here. Where is our streams application? Whether timestamp extractor. There's a thing getting popping out here. Implements timestamp extractor from Kafka, which implements method extract that takes a record. So each record that goes through your application is passed through here, and its key and the value, of course, right? And you need to help to give Kafka time of that record. You can somehow derive it from record, or you can use partition time, or whatever you want to do. So in our case, because we have different classes that are going through Kafka, like weather measurements, weather average, and so on and so forth, let's create an interface. Let's create an interface called weather timestamped. I told interface, right? That has a simple method, long get timestamp. And our classes are going to implement this interface. Yeah. because it's from block, it's just not obvious, but I'm going to do it like this. Okay. Override timestamp, just to make it clear. So we're going to use milliseconds as a timestamp in Kafka, and also we're going to give our average here same timestamp. Implements timestamped. And I forgot to add it here actually, right? To epoch millis. And probably something got broken here, right? I need to give it a timestamp. Let's say the timestamp of the aggregation is the time it was aggregated. End time. Good. Okay. It looks good. Yeah, but now that we defined extractor, this one, we need to. Sorry, we haven't defined it yet, actually, right? We need to define it. We need to take record value if record value is instance of whether timestamp. I haven't enabled preview features, so it's just whether timestamped. Then return whether timestamped value get timestamp. Or if we're not lucky enough and just some another thing here, log barn strange class here, and we return system current time. Okay, and we need to help Kafka streams a little bit. We need to actually define the binder configuration, default timestamp extractor. I need to give it this. Why is this thing popping up again? We need to give it this class, so it uses it. And let me rerun our streams application. Some exception. Because timestamp is null. That's interesting. That's why. That's because we have some old messages in there that were that got into Kafka without this timestamp field in there, right? So we have some schema migration task going in here. Let's just do it very simple. If timestamp null, then system current time mills. If not, then use this one. Not something probably you want to do in production, but still, that's how we do it. That's how we migrate schema here. Okay, looks good. Looks good. So we have defined this thing. Going back to our presentation. Yeah, one more thing to understand with a string time is that Kafka Streams understands what time is it now only when a new message arrives. So it doesn't use your computer's clock. It doesn't use it. It uses time of an event. So at any moment of time, Kafka Streams thinks that the current time is the largest, the newest timestamp it ever seen. Okay, so it derives time from the records, not from the clock on your computer. And knowing that, let's test an offline scenario. Let's simulate some interesting thing. What if our IoT sensor got offline, right? Maybe you have some, I don't know, some sensor somewhere in on a ship somewhere near in the Pacific Ocean, and it just got disconnected from the internet, which is okay, right? And when but the data was still accumulating on that ship, and when it got online again, when it got into some port, it just streamed all the data again. And we want to make sure it works. Just let's test the scenario. Let's see how it goes. So I have here actually two instances of weather sensors. I will launch them. And the difference is that one of them uses localhost for as an address of my REST application. Another one uses weather station DNS name, host name for sending data. That is actually equals to localhost as well, right? As you can see. So it works. It should work. We see weather measurements from device 1. That was the first one, and very soon we will start seeing messages from a device with an ID 0. Let's wait a second. So let's actually. Yeah, so here in the aggregation, we see device 0, device 1, device 0, device 1 seems to work, right? Now let's try to emulate a disconnection, a loss of connectivity for one of those devices. And I'm doing that very simply. I'm just changing a host name here, and we'll see that one of the devices. Yeah, so this one, you see, it stopped sending measurements. No sent measurement anymore. So it's now offline, though it still generates some data. And the code is written in a way that it stores them in a queue, and it will push them, it will like pop them once it gets online again. So let's try to fix the connectivity for that device. And because it's Python, it's just not so quick as Java. And of course, it's not because of that, but we'll see that it got online again and sent measurements in a minute or so. So let's just wait here for a sent message. I believe there is some exponential backoff or something like this going in Python library I'm using for sending data. And that's why it just has some big pause until it begins to send data again. Yeah, it's all the time I'm testing this thing. Yeah, I got another sent measurement. So okay, it started sending data, and let's see our logs of our application. So everything looks good, like no errors, looks fine. Here we see device 0. We again see messages from a device 0. So it looks like this use case worked fine. It looks like everything is great actually. But if you're doing something like this in production, you have like big problems. So let's try to actually enable login level for org Apache Kafka Streams to debug. Restart our Streams application. And simulate the same case. So I'm going to send one of those devices offline, changing the DNS, changing the hostname mapping here. Okay, it stopped. I think it's fine. And now let's fix the internet for this device. Once again, we need to wait a minute or so for this thing to get back to life. Come on, it's Python. Never as quick as Java. Yeah, make sure we see logs here in our streams application. I don't know if it's an oh yeah, finally we got messages. We got some logs here. Oh my god, you know what? You won't see what I wanted to show you because wrong name here. Extractor. It's actually not uses our weather timestamp extractor, right? So yeah, that's a problem. That's a problem. We have to restart it. So always test your code, right? Always make sure what you wrote there actually works. Okay. Again, quick disconnection for our device. Let's wait actually just 5 seconds and bring it back to life. Yeah, so here now it sees where there's some type of extractor. And again, we're here waiting for this Python library to came live again to start sending data after disconnect. Come on. I'm not sure it's actually an exponential backoff. It looks like it's just some static backoff after it got some error and just waits for a minute or so. Okay, send measurement. Boom. That's what I want to show you. Skipping the record for expired window, and it's you didn't see that on an info level. You see, that's a problem. Actually, records that arrive from the sensor that was offline, records that were generated during its offline period are skipped. They didn't get to your application. It just Kafka Stream just dropped it out, and it might be a big problem for you. So I was working on a project involved in collecting health information, and we saw this problem. Luckily, we saw it not in real patients, not in real world scenarios, but it's a big problem. And I will tell you why it happened and how to fix that. So once again, messages sent by a device that was offline are skipped. They are just skipped by the Kafka Streams application, and you didn't know that unless you enable this locking level. So it's only possible to make sure you didn't skip them by having some testing in place, by just making sure it's in somewhere else. Let's discuss what happened. So expired window, why? The problem is that stream time is tracked per partition, not per key. If you remember, I told you that Kafka Streams thinks that the current time is equal to the largest time of the last event it saw. And because we get two devices, the one that was online all the time, the green one here on the picture, and the device that was offline for some time, the blue one here on the picture. The Kafka Streams saw newer messages with newer timestamp for the green device here, and it just advanced the time. And when it got messages from with an old timestamp, those that were collected during the offline time of the device number 2, it saw it. but the time is already more than 15, like on this picture, and it just got rid of them. So the problem is that the stream time is tracked per partition. So actually, if you have many keys, many devices in this case, sending data to one partition, which is a very common scenario, and that's something you want to do, you might have some problems if you have offline generated data. So there is a ticket in Kafka Jira where there is some discussion about this, and that some ideas that maybe there should be an ability to track time per key, not per partition, so there will be no collision of times for different devices. But this is not something that is there yet, although there are some solutions. So you might wonder, so okay, what's now? So Kafka Streams doesn't work for Internet of Things or other use cases where you need to generate some offline generated data that was sent just too late. Actually, there are solutions. So first, you can create a custom operator that implements that basically you can implement a custom function in Kafka Streams that can track time per key and not per partition. And I actually pushed an example of that with this long name of the class in the GitHub repo. You will have a link after this talk where you will see a solution for that problem. And really, if you work with IoT or something where you have offline generated data, this is the solution you really want to check this out. Another solution, of course, to wait for a solution from the Kafka team. Although it's almost a year since this ticket was created, and I was participating in discussing that with Kafka team, and unfortunately, there is no solution out of box at the moment. And of course, there is always another solution. So because the time is tracked per partition, you can create as many Kafka partitions as there are keys, right? So you will have a separate partition for each key or for each device in our case. So time will be tracked separately. And of course, that's not very sophisticated solution, and you'll get problems scaling it out. But if you don't have a lot of keys, then why not? That's easier than writing some custom code. You can just do this thing. Yeah. One more interesting use case. Now that you know about K stores, about those K tables, right? Kafka state stores K tables, you can organize tables in Kafka. So even though Kafka is everybody thinks about it as a queue, as some log stream of messages, it actually can be used as a database with a table. So let's see an example here. So on one of my projects, we had a problem. We had so each rectangle here is a microservice. So we had some source of possible duplicates. Some microservice upstream was generating duplicates, but it was only possible during 5-minute window. So after 5 minutes, no duplicates. But during those 5 minutes, some duplicates were possible. And on the bottom, we had consumer who doesn't tolerate duplicates, who really will fail, and the whole business will struggle if some duplicates will get in there. So what was implemented before I came there and we started thinking how to fix that. There was a deduplication implemented in the PostgreSQL. So for each key sent to Kafka topic, to microservice number 2 here, there was a Postgre tracking each key. And when duplicate arrives, you're going to PostgreSQL. You see if this key is set to processed, right? If it exists there, then you kind of skip it as a duplicate, right? And if it's not there, then it's first time, and you write it to Postgres and you send this thing downstream. And those of you who are into distributed systems probably saw a problem here already. The problem is that let's imagine a scenario that we have a message that goes here that writes its first time, right? It writes the second microservice writes its key to PostgreSQL, and then it dies. The microservice dies. So you already have a message in PostgreSQL, but you haven't sent it downstream, right? So Kafka, for example, let's say our Kafka message wasn't committed, your Kafka transaction, and so this second microservice gets this message again, right? It gets it again, it goes to PostgreSQL, and it sees that it was processed already, and it skips it, right? So it's just you lose this message. This message is not sent downstream. You can say, okay, let's swap these things. Let's first send it downstream, then write to PostgreSQL. Okay, in that case, again, what if your microservice dies in between? So you have already sent this message downstream, but you haven't written that to PostgreSQL, right? And same again. Now, new message comes here. It sees that in PostgreSQL there is no record of that, and it sends again. You get a duplicate. So what? So you have basically two ways to write a code. One that potentially loses the message. Another one that potentially creates a duplicate. Right. The problem is that sending message downstream and setting and writing that to PostgreSQL is not an atomic operation, and it can be broken in between, right? So a very cool thing in Kafka Streams that helps you to solve this is a case store. That's what I told you. So the cool thing is that you can actually replace PostgreSQL in that case, or any other, let's say, relational database, for example, or any other database with Kafka Streams state store. So you have same table that we got in PostgreSQL, but now in the Kafka Streams. And the cool thing is that now you can use single Kafka transaction for committing incoming that you received incoming message, writing that to a deduplicator tracking table, and also sending this message to the downstream as a single transaction. So all steps 1, 2, and 3 are becoming a single Kafka transaction. Those are now atomic operations. Those are all are applied or all are rolled back, and that's a very cool thing. In many cases now, if you have some tables in remote in third-party databases, you can now replace them with Kafka Streams table and utilize a common transaction, a common atomic operation to make sure you don't have duplicates, you don't have lost things, and you're getting exactly once here, and you're getting deduplication. It's very cool, and it works on top of Kafka transactions. You better go and read about that before you implement those things, so you understand only how it works, and you need to make sure that you deliver to Kafka and not to HTTP, for example, or something like this. So just go and read about that. There will be a link in the end. In order to basically you enable this use case, in order to make everything in a single transaction, it's very easy to do this in the Kafka Streams application. You just need to enable this option, this long one. I'm not going to read that. Set it to exactly once, and you'll get transactions. You'll get every incoming and outgoing message reading in a single transaction and committed as a single transaction in Kafka Streams. So let's try to enable it. So it's configuration here, processing, guarantee. Oh, make sure you write it correctly here, or you will not get the transaction. You might have problems here. So restart our Streams application. Not sure it's it's written here. Good. And by the way, we will also see. Yeah, let's wait till it starts. An interesting thing here, after you enable the transaction, is that now messages for each device are sent one by one. Remember, previously we got a 30 seconds commit interval in Kafka, so we got all the messages in batch. Now, because you have enabled transactions, Kafka Streams commits for every message it got, right? Because every message is a separate transaction, is a separate atomic operation, and it now commits them one by one. So now you got this real-time processing with no batching, and it's just that simple. So you get exactly once, and you get like real time. with one option. It's very cool. Yeah, so last but not least, things to know when deploying to cloud. So first of all, make sure you're using one of the latest Spring Cloud Kafka Streams versions, because Spring Cloud Actuator Health Endpoint didn't track Kafka Streams liveness before version 3.0. And you know what? That means that if you get an exception in your Kafka Stream processing logic, this Kafka Stream thread just dies and it sits silently in there, and your application is still running. It's not going to shut down. It's not going to die. It's not going to inform you. No, there is a log, of course, but are you tracking logs all the time? So make sure you are using latest version with a health endpoint. Actually, health endpoint tracks real liveness if there are any problems with your application, and make sure to restart it once your monitoring system got this problem. Also, it's better to have the same persistent temp folder. Remember, that's the folder that stores those intermediate aggregation states between application redeploys, because it helps Kafka Stream to recreate state stores immediately, as opposed to rebuilding from the changelog topic. So if your Kafka Streams application dies and it got some state in those state stores, and when it recreates, let's say your Kubernetes schedules a new container, right? If it sees the same TMP folder, it will use it. It will use the state in there, and just it will start very quickly. But if it doesn't see this TMP folder, it will go to Kafka Stream changelog topic, where the state is backed up, and it will reconstruct the whole K table in this store by reading one by one all the messages in the change log, which is long. So that's why it's better to make sure your local, the place where your state store is stored, is visible between redeploys, between rescheduling of your application. So it's, for example, you might consider deploying to the same node, or you can use stateful sets in Kubernetes and it will do it for you. Yeah, and that's actually it. I hope you really enjoyed this talk. There are a lot of questions, of course, and topics I could cover, and hope to have a nice, cool discussion after this talk. Here you can find some QR codes for examples for the code I wrote here in the middle. There is on the left, there is also a QR code with the Google Doc that contains links to some topics articles that explain some things I showed you here in more detail, so you can really nail those topics. And on the right, there is my Telegram channel. Please subscribe, and from time to time I'm posting there some interesting things that were not covered here, some deep dives and some cool things. That's actually it. Thank you.
Thank you, Dmitry. Thank you for this deep dive, and you can continue the communication with the audience in your Q&A Zoom room, and also answer all the questions here. Thank you very much.
Thank you. Thank you too.